questions to the end if there are some questions for the three panelists this morning. Our next speaker, again, is familiar to, I would imagine, most or a lot of people in the room. He hails from Scotland. He is a structural engineer. He started his high-rise career out in Hong Kong on Norman Foster's Hong Kong Shanghai Bank building, their seminal building with the firm Arup in the 80s, and 30 years later, more or less, he's still with Arup as a principal in the New York office. I remember, again, at the 2006 conference, David was working with Daniel on several schemes, and Daniel introduced David as one of the world's greatest structural engineers working at the time. And I was very privileged to work with David as he was chairman of the council from 2006 to 2009. Can you please put your hands together for David Scott?
Good morning, and thank you very much. It's a great pleasure to be here, and a great honor for me to give a keynote, and very daunting to follow that wonderful speech by Daniel. I've been very fortunate over the last 10 years to actually go with Daniel on part of that journey, and I think that some of the projects that we've done together have been wonderful, exciting, and when you see some of that work, some people say, well, this is crazy, this is very expensive, but actually there is a lot of efficiency within there, and these buildings are much more economic than they may look, and I'm going to talk a little bit about that later on. My talk will focus on some of the trends that we're seeing going on around the world, both in design and in the design for safety. And it's interesting to note that as engineers become much more sophisticated in being able to model and analyze tall buildings, you would have thought that we would be converging on solutions, standard solutions, at least in terms of quality of safety that we are able to give in different buildings. After all, the value to society of human life and the value to society of cities is the same in America, same in Korea, Japan, Philippines. Every country in the world actually values its people and its cities the most. So it's quite surprising that as we understand buildings and how they perform, that we actually haven't got a similar standards across the world of actually meeting safety. And I'm going to talk about that later on. An increasing part of our business is actually refurbishment, and I hope the same applies to many of you here, because it's through refurbishment of the existing building stock that we probably can make the biggest difference to the world's environmental sort of footprint or carbon use. And indeed, if we can upgrade our tall buildings in areas of severe seismicity, then that is also a route to creating a sustainable future in the process that we use for tall buildings is one that we've developed for the Property Council of Australia. And I would suggest that you look at that on their website, because it's quite a comprehensive method of assessing and evaluating the performance in tall buildings. And the council, this council is working with the Property Council of Australia to actually see if we can take this method of evaluating buildings and coming up with recommendations for improvements, and actually following similar processes in buildings around the world. So that potentially is very exciting, both for the council and for the future of tall buildings. When we look at these buildings, we create a comprehensive assessment of both the condition and the performance of the buildings. And we go and look at all aspects of it, looking at ways of upgrading everything from boiler replacements, solar power, upgrading metering and lighting systems, essentially a comprehensive evaluation. And for each one of these, we create an assessment of the cost of implementing an initiative. We make an assessment of its neighbours increment. Now, neighbours is essentially a cross between LEED and Energy Star. So it's a comprehensive evaluation of sustainability. And we look at annual savings in energy. And then we sit with the developers and work out what the most effective way of implementing the retrofit is for the developer. Because in Australia, like many countries that care about their sustainable footprint, people only want to go in, live in, and work in buildings that are sustainable. There is a big difference in the rent and the occupancy in buildings that perform well and buildings that don't. And the wonderful thing about this process is that the outputs are in the public domain. You can evaluate and see exactly where your building stands. And you can see here that we're targeting a reduction of about 40%. That's about 1.2 megawatts on this building per annum. And you can see the light blue line is our target, and we're on target to actually meet this. The same kind of thing exists in Europe, where buildings that have low occupancy, high maintenance, are essentially, developers are looking for ways to refurbish them. They cannot attract the occupancy they want to make them valuable, but modern buildings are so much better that they're looking for other ways of repurposing these towers. And this is a wonderful scheme by Wrightfield Architects of that building that you've just seen, of installing modules into it and transforming it into a residential building. Being modular construction, the modules have the toilets and the kitchens and can be simply inserted into the buildings to make actually quite a different type of building to what it was before. Modular construction is something that we are seeing more and more of, and this is a 33-story building that we're looking at, which is completely modular in nature. And this is part of the erection sequence. It's a steel frame. The modules are self-supporting. Over the last 10 years, Anthony said that some of these are perhaps crazy, but actually many of them are being built. And what is very interesting from my perspective, there's a lot of Daniel's work in here, is that you can make these buildings much more efficient than you possibly think they are. You can also make them very inefficient. And the best way of achieving a good design is if you can integrate the architecture and the engineering together. The Twisty Dubai Towers project, for instance, we could actually save half the cost if we made small changes in geometry. And that's what we did. Unfortunately, that was cancelled due to the downturn. Yesterday, we heard the keynote presentation about this project, which we designed in our New York office, Boston office, Singapore, Hong Kong, UK office in a collaboration. Unfortunately, when we won the project, the developer had agreed completely on this form, and we had no time to actually refine it and develop it. We just had to make it work. And who would have imagined that this could be built in 27 months? I think that Sang-Young did a wonderful job, and it's much more difficult to build this in 27 months than it would be, in my view, to build a 100-story straight building. The challenges here were quite phenomenal. This is one of the early BIM models. The later ones incorporated everything. And here are some of the temporary works needed to actually create the tower of this size. The contractor said that the architect was perhaps very inflexible, but we had to create exactly the same shape that the architect had dreamt with. And we would have only actually ever able to achieve this by a strong collaboration between the engineers and the contractor. and coming up with a way of instrumenting and documenting the building movements as it's built. This was a fantastic achievement, both by the Korean contractors and by the whole of the design team. Daniel just talked about this project, Slotty 54, and given an example of how it's showing some later photographs than this. But again, what is the premium that this kind of geometry costs? And I think that there certainly is a premium, but perhaps it's not as substantial even as the premium between good ground and bad ground. So you have to go into these types of buildings with your eyes open, and there are opportunities. I love this building. This is another one of Daniel's buildings. Because of the juxtaposition of the square box and modern architecture. Both these buildings are very economic. There is very little cost premium between one and the other. And which one would you want to build? And which one is really exciting? Because Daniel's building is essentially just a curved form. It's flat glass. It's got balconies that step up. And one of the walls is is leaning out at about 5 degrees. Very simple to build, very fast to build, but really very dramatic. This is another building that we did with Aldar. Again, it's a case of integrating design with construction. We came up with, from the concept to the time we completed the course was 12 months. And again, we used modular construction, dropping the modules in from the top of the building, fully fitted out bathroom units, fast and efficient. And this is something that a tower we developed with HOK. Hopefully it is the next tower to be built at Songdo. It was the one that was going to be built when the crash came in 2008. But again, the amount of concrete in this tower compared to a square box giving the same area, it's exactly the same. This is made out of flat and vertical concrete. It is simple to build, and hopefully this will be the next off the block out at Songdo. And I'd encourage you to go and have a look at some of the work out there whilst you're in Korea. Really, there is some marvelous projects. We're working, I'm going to change tack a little bit and talk about some structural aspects. Viscous dampers are becoming increasingly visible in many tall building projects around the world. This is the pinnacle that we're doing with KPF, a 2,000-ton saving in structural steel. Again, it's a very complex form, simply because London would not allow a square boxes in there because they think it is unacceptable to actually put that type of thing in the environment. So this whole building form is related to the place, it's related to the cities, the views and the perspectives seen from all perspectives. And we've put in the perimeter wall these viscous dampers that increase the total damping capacity. The viscous dampers reduce the amount of wind loading that the building sees and also therefore reduce the accelerations, giving us a saving. And because we've got a large number of dampers, there's a lot of redundancy so that we can actually rely on them in wind and in other conditions. These dampers don't just help small buildings, but they help any building where wind accelerations or wind forces due to vibration are a problem. This is a tower that is under construction. It did stop for about 2 years. It's now up to level 3. It has recovered from the recession. 40-story building, and there was a problem with wind accelerations. It's a steel core only building. Small problem with wind accelerations, and we had an opportunity to add in 500 tons, but we didn't. We put the dampers in, that improved the overall performance, and we took out 500 tons. So a total saving of about 1,000 tons of steel, a big deal for this client on a small building, and there are more and more opportunities for viscous dampers to improve performance. Interesting that There is a debate within the industry about what is the appropriate damping levels in buildings from the buildings themselves, and I hope this is something that the Council will encourage its members to collect and monitor data on buildings, because these are the measurements you can see of many buildings at heights over 250 meters. The damping under small movements, this is not under extreme movements, is less than 1%. So I know that many people are monitoring, and we would like to encourage and see more of that. Wind loads in tall buildings are usually dependent upon its damping. An increase of 1% to 2% can actually reduce wind loads and accelerations by more than 20% in a building that we're working on at the moment. But the damping does increase as the movements increase, so perhaps existing values for strength are okay. We need to build a consensus, and this is something that the Council can participate. On this tower, it's been talked about before in one of the sessions, St. Francis Tower in Manila. We put in dampers for typhoons and dampers for seismic. And this building had been designed originally for using prescriptive codes for seismic design. And we developed a performance-based design approach which reduced 30% of the concrete and saved 40% of reduction in rebar and had 16 dampers in it. But the problem was that the code design did not work. The shear demands in the building were much higher than the code predicts, and the code design would have been ductile and unsafe. It would have been non-ductile and unsafe. The proportion of the shear taken by the perimeter frame was actually nominal, and special design of the core is needed in this type of condition to give the modest plastic rotation that would not have been identified by the code. So, as you probably know, this document has been produced by the Council. It is a recommendation essentially that says if you're in an area of severe seismicity, you should be using performance-based design. And then at yesterday's session, Ron Klemenchik showed the peer document which actually takes you through the way of doing it. A very good document and can be downloaded for free from the web. So here are the dampers, a much improved performance. This is looking at it under a 2,475 return period. The higher modes dominate behavior, and the higher modes movements are not picked up in the code design. This is one of the big issues. So talking about diverging approaches to tall building safety, and this is the crux of the things, one of the things I'm most concerned about. Some countries, including parts of the US, still do simple prescriptive codes. And this can be unsafe. It's certainly not our recommendation. Why do architects and engineers do it? Well, for many reasons. Quite often we're asked to by developers that don't know any different. Sometimes architects or developers are not willing to pay additional money to do complex design. Perhaps some of the engineers don't actually understand the values and benefits, but it is a real issue that we are potentially designing buildings that are unsafe. And architects need to understand their obligations in severe seismicity, particularly when they're lead consultant. Both you need to understand the safety values, you need to understand what the risks are, and you need to understand that seismic design is a holistic approach. I've seen so many conditions where engineers create something and architects will then put in a non-structural wall or a concrete wall that may change completely the performance of the buildings, that can affect the seismic performance. So you need to be involved in the process, you need to understand the risks, and you need to understand the different methodologies in doing this design. There is a 3-level approach: service level, design level, maximum credible earthquake level. And I'd like to question the big divergences in international practice between Japan and China and the US. We're all on different paths. And at yesterday's meeting, the seismic committee led by Ron is saying that we're going to try and collaborate to work out appropriate design methods that are consistent for all of us. But I think one of the most important things is to actually determine what performance objectives should there be and what performance objectives are appropriate for tall buildings. You know, the process that we use in the States has been developed over 50 years, but people's expectations of what engineers do in tall building design are changing, and people expect tall buildings now to be safe and to perform, and we need to understand and have a discussion with society about how we can do that. So at a service level, which is a 50% probability exceedance in 30 years, we expect an elastic response. But how long is a building going to be operating at its service level, and why only a 30-year return event? The Empire State Building is a grandfather of tall buildings. It's been going for 90 years. It can go for another 110 years. So perhaps we should be looking at the events that occur over a 200-year event as being the service level event. This is something that we need to get our heads around, and we haven't. And for the maximum considered earthquake, the code approach in the US is for the maximum earthquake that perhaps there is a 10% probability of collapse. Is that acceptable? We have very large deformation limits. Are they acceptable? Japanese codes and Chinese codes are much more onerous. In 2008, PEER, the American organization, did a review of performance objectives. And they asked owners and developers what they thought about the possibility of collapse. And these are some of the comments from the PEER document in 2008. That a collapse of a tall building is unthinkable to the public. Tall buildings should be considered a special class of buildings. They have a greater impact on the city than other buildings, and the limited exits mean there should be increased resistance to damage and fire. Loss would be devastating. The recommendations in PEER was that this is a public issue and should be debated publicly. Well, in the last 3 years, I haven't heard very much debate about this. This is something I think that the Council should have a view, and it is something that we should work on a broad international basis to try and reach a consensus of what is important in areas of severe seismicity. There are 4 performance objectives that you can do if you follow the PEER detailed guidance. Essential facilities, immediate occupancy, life safety, collapse prevention. The Arab standard approach is to recommend life safety as a minimum standard on tall buildings. So the collapse prevention is more equivalent to the 10% probability of collapse under the extreme event. Life safety is better. The Chinese practice, although it's not explicit, perhaps is more akin to immediate occupancy, because they put an enormous amount of material into their buildings, something which I disagree with, and I'll talk a little bit about. They have extensive requirements both at level 1, 2, and 3 seismic events. Their general requirements are, you need to have a dual system. It needs to attract a portion of the load from top to bottom. No sudden changes of stiffness. The forces are much larger than the UBC forces. The maximum drift is much higher than, or a much smaller drift than we would permit using the standard US approach. And what's the overall result? Is that buildings, some of the big buildings in China probably have twice as much material in them for the same seismic load. And that may be an overall premium of 15 to 20%. And what do you get from that? Well, you get less damage in a normal event, inevitably, maybe not a lot less, and you get a better performance in an extreme event. Without doubt, that is what happens. Now, my view is that that perhaps is not a good value for the Chinese. This is a 560-meter tower that we're looking at, 3 million square feet, 110,000 tons of steel in it. And the elements are enormous. 4.6 meter by 4.6 meter columns at the base, with lots of steel in it. Steel sections, not steel plate. The core itself is 800 thick, but has steel plate running in it for the first 300 meters of the building. You know, if you can take 50% out of that, that's 55,000 tons of steel saving. The only people that are happy with this design are the steel companies. You know, the amount, its performance is not that much incrementally better. And so that is partly why we're looking within the council to try and reconcile the performances. Oh, and it didn't work, by the way. There's still at the top, there was a requirement for the frame to take more shear load. Again, this is not, Dennis is from TT is nodding his head. It's the type of thing we face all the time. It is a problem in getting economic buildings in China. Japanese practice since 1981, again, it's much more severe, much more onerous, and we hope that Japan, China, US practice, and Chilean and all can come together to create some clearer recommendations on performance objectives. But it is performance-based design that allows us to do some very interesting things. This is a tower that we're doing with Benjamin Romano. It will be the tallest building in Mexico, and it is quite an unusual shape, and it's only through performance-based design can we ever consider looking at very complex buildings like this to actually get them built and designed effectively. What was quite interesting to me is that these are the design spectrum, and here you can see the surface spectrum. That should have worked. Let me try and unfortunately, the movie's not working. But there was a significant benefit of doing a 3D soil structure interaction analysis. Mexico City has 10-story basements for parking, are quite consistent. And when you looked at the 2D effects, that was one thing. When you looked at the 3D effects, that gave you substantial savings, particularly in the 1 to 3 second range. This building has just completed its independent peer review. And what's really cool about it is underneath the building, we're doing a bit of historic preservation, because we had to take this building and move it 30 meters in one direction, build a basement underneath it, move it 30 meters back, and underneath this large legs of this tower, we're going to have this historic building. Professor Wada mentioned yesterday about some of the seismic isolation in tall buildings. It's not something we would ever consider here, because it's all about reducing damage. What level of damage is acceptable? And clearly, Professor Wada showed some small cracks in a building and said, people do not want to live in this building after these cracks appeared. And this is not like the level of damage that we're considering that may occur if we say a return period of 50% probability in 30 years, then we're talking about damage that may occur in 200 years, 6 or 7 times. It's an issue, and I think we need to have a consensus. We did this building in '98 with a rocking base. When we tied down the footings, we could not get the building to work. But actually, when we lifted off one of the footings, the building worked very well. And so we used a damper at the base of this building, and we got performance. And so we've been looking at the same type of detail with tall buildings. You know, Tall buildings under normal wind loads and indeed seismic loads, they generally don't have any, well, under normal wind loads you don't get tension typically in the base of the core. Under seismic loads you can get very large forces because the base is fixed. And this is us looking at a way of perhaps developing a rocking system. This is, without rocking, this is yield forming in the base of this building under a severe event, and what you would do is detail it to generate yield in the small amounts of movement in an effective way. And then this is one of the alternatives, which is rocking. It's under the same time history, and you can see that the edge of the core lifts off and down. And this building is still stable, it's more effective, gives you a more reliable performance. There are a few details still to work out though before we can go ahead. But this is the type of thing that can potentially, with dampers, give you better performance on tall buildings. So, in conclusion, and I won't talk to you about fire engineering, but the same thing exists. Specifically modeling fires can actually give big advantages, and I'll just whiz you through the slides. But on seismic design, 50% of the world's cities with populations exceeding 2 million are at risk of earthquakes up to 7.5 on the Richter scale. And perhaps the slide at the background, is that level of damage acceptable? Is that life safety? Well, people got out of it, but what would the loss would be devastating to people who had a building like that, because it's just going to be taken down. There are increasing expectations, and over time people's expectations increase about what they expect from architects and engineers, and the council should have a view on what levels are acceptable. And so the same applies to fire engineering. Performance-based approach can give you better performance, less cost, less money. And this is just some of the work. This building did not work to code. When we did the performance-based analysis, but we put more fire protection on some elements, took it off others, we got a better performance with less cost. We've done this, we're currently doing the analysis on the Pinnacle, and we know that buildings like this will not perform well in fire, and we know that WTC7 did not perform well in fire either, and there's various explanations for that, why that happened. So overall conclusions, performance design of extreme events can lead to better performance, less cost. It's the way to go. We have tools that can model blast, fire, earthquake impact. We need to develop methodologies that everyone can use on earthquake to get, not just the elite consultants, but everyone can use to get performance on in earthquake zones. And we can test our buildings for extreme events before they happen. That's a big difference, and we should be testing our buildings. We need to build up an international consensus on the performance requirements, and viscous damping, it's the way to go. There's a lot of economy there, and you'll see more and more of that in the future. Thank you very much.
Thank you, Dave.